Imagine you hire the smartest assistant on the planet. But there's a distinct catch. They have zero short-term memory.
Right, like a complete blank slate every time you talk to them.
Yeah, so every single morning, you have to explain the precise mechanics of how to make coffee, down to the smallest detail.
They can brew a flawless espresso, sure. But if you, say, omit the instruction to place the cup under the machine first, you just end up with hot coffee poured directly onto the counter.
Because the intelligence is there, but the operational awareness is just completely absent.
And because you spend so much time explaining these microscopic steps, you realize you haven't actually saved any time at all. I mean, you are exhausted before the day even begins.
Which is not just a sci-fi hypothetical about a kitchen appliance. It is the exact frustration that knowledge workers and developers are facing right now with generative AI.
The manual prompting fatigue is very real.
It is. And today we are taking a deep dive into a massive structural shift intended to cure that fatigue. We are looking at a collection of technical blogs, enterprise case studies, and VC insights to explore how we are moving away from manually typing prompts.
We're transitioning to designing autonomous systems that basically manage the AI for us. It's called loop engineering.
And our mission today is to understand why loop engineering isn't just a new coding trick. It is a fundamental shift in management philosophy.
It really redefines the role of every professional in an AI-native environment because human responsibility is migrating away from executing tasks toward architecting systems.
Let's ground this in a specific inflection point from the source material. Look at what happened in June 2026. Boris Cherny, the head of Claude Code, made a statement that acted as a wake-up call.
Right, the quote about not prompting anymore.
Yeah. He stated, "I don't prompt Claude anymore. I have loops running that prompt Claude and figuring out what to do. My job is to write loops."
Which is a profound shift. We need to define the mechanics here, though. What actually separates a loop from just a standard, really good AI interaction?
In a standard interaction, you're the engine. You type a request, wait, read it, and type the next one.
But a loop is a continuous, iterative execution cycle. The system is designed to perceive its environment, reason about the problem, take an action, and then evaluate the result of that action.
And it just repeats that cycle until a specific goal is met.
Yeah. The machine replaces the human as the connective tissue between turns. You step back from the chat box and you build the machine that runs the chat box.
Think about a ramen shop. Manual prompting is like a customer standing at the counter ordering a highly customized bowl of ramen every single time they want to eat.
Specifying the noodle firmness, the broth temperature, every single topping.
Every single visit. It requires high effort from the customer for every unit of output. The leverage is terrible.
Because the output scales linearly with your physical input.
But loop engineering is like shifting from being that customer to being the shop owner. You aren't ordering the soup anymore. You are designing the operational rules of the kitchen.
You decide when the prep starts or at what interval the sous chef needs to taste the broth.
Or the exact protocol for escalating a customer complaint. You design the systems of the shop runs without you standing at the counter.
To understand why this shift is happening right now, we really should trace the historical evolution of how humans have delegated work to AI. The sources outline a clear 4-stage progression.
Stage 1 was prompt engineering, right?
Yeah, stage 1 was purely about optimizing conversation and wording. The human performs or directly guides the work turn by turn. But as models improve, spending an hour tweaking adjectives just stopped making sense.
Yielding diminishing returns, which forced the move to stage 2, context engineering.
Instead of optimizing the wording, we started optimizing the information, feeding the model's project files and utilizing retrieval augmented generation or RAI systems.
So giving the AI a dynamic reference library to read from before it answers, we were still directing the work, but providing a richer background.
Which brings us to stage 3, harness engineering. This optimizes the environment itself.
Setting up the guardrails.
Right, the guardrails, the available tools, and the secure sandboxes that a single agent runs inside. The human role shifted there from directing the work to supervising the environment where the work happens.
Leading us finally to stage 4, loop engineering. Optimizing autonomous execution, where we design systems that perform the work themselves.
There is an active debate in the tech community regarding where this actually sits in the hierarchy, though. Adi Osmani, an engineering lead at Google, argues that loop engineering sits a layer above the harness, like an overarching orchestrator.
But Gerald Chen pushes back on that in his writings. He argues that loop engineering shouldn't be a separate layer above, but rather the most critical subset inside the harness itself.
It's an interesting friction point. but the exact classification feels less important than the functional reality.
Right? Whether it sits above or within, the outcome is identical. Human responsibility has fundamentally shifted from operator to manager to architect.
We are delegating the iterative cycle itself. And this evolution isn't just about software capabilities catching up. It's actually a necessary response to a biological bottleneck.
A biological mandate,
Yeah.
essentially. We had to invent loops because our brains physically couldn't handle the alternative.
The modern knowledge worker suffers from chronic cognitive overload. Information just outpaces our structural capacity to process it. And conversational AI interfaces, ironically, they exacerbate this problem.
They demand incredibly high energy from the prefrontal cortex, the brain's executive control center.
When you are prompting manually, your prefrontal cortex has to hold the overarching goal in working memory, track the context, read the outputs, evaluate for errors, and decide the next step.
It's a massive cognitive drain. Sparing the prefrontal cortex from that reactive, repetitive task execution is the primary biological benefit of loop.
By externalizing the planning, execution, and verification cycles to a machine, the human brain is freed from that micromanagement loop.
We can frame this through Clark and Chalmers' theory of the extended mind. The Thule loop becomes a cognitive prosthetic. It functions as an externalized component of your own thinking process.
But I could see someone challenging this framing.
I would challenge it. If we are offloading the planning and the checking, isn't this just a sophisticated rationalization for laziness? I mean, are we just building machines so we don't have to engage with the hard work?
It's a reasonable suspicion. But the neurobiological perspective offers a different interpretation. Sparing the prefrontal cortex doesn't mean the brain just turns off.
Energy is reallocated.
Well, it's shifted. When you reduce the cognitive load of repetitive execution, you activate the default mode network.
And the default mode network is the brain's engine for creative incubation, strategic synthesis, deep concept integration.
Human intelligence is biologically built for synthesis, not for repetitive high-speed task execution. So loops actually align our daily workflow with our biological strengths.
Okay, so if we accept that this biological relief is necessary for an individual, we have to look at what happens when you scale that relief across a massive organization.
The Meta case study from the sources illustrates this perfectly. They deployed what they called an agentic second brain to 60,000 knowledge workers.
And this wasn't just isolated to software engineers. They rolled it out for marketing, human resources, project management.
The interface they chose for this is critical. They utilize the PRA workspace. That's projects, areas, resources, archives.
Which is a folder structure originally designed by Tiago Forte for human note-taking.
It turns out organizing information logically for a human is also the perfect interface for an autonomous agent because it provides explicit semantic categorization.
When an agent enters a workspace, it needs to know what is active, what is reference material, and where to put new information.
And the PRA structure facilitates a principle called progressive disclosure.
Because if you dump an entire corporate database into a single prompt, the output quality degrades rapidly, token costs explode, and the model just loses track of the instructions.
But the PRA structure allows the loop to load context dynamically. It retrieves deep details only when the specific task requires it, navigating the folders just like a human researcher would.
The implication there is that the primitives we use for coding loops map perfectly onto general office work.
Right. In software development, you use work trees, isolated file environments, so agents don't overwrite each other's code.
At Meta, those coding work trees just became isolated task folders for HR or marketing projects.
A skill in coding might be a syntax rule for Python. For a general knowledge worker, a skill becomes a brand editorial guide or a legal compliance checklist.
And connectors shift from Git repository commands to Slack APIs and document editors. The architecture of autonomy completely transcends writing code.
Autonomy, however, is incredibly expensive. We have to look at the economic realities of letting these loops run wild.
Look at the deployment at Uber. They rolled out coding agents and exhausted their entire annual AI developer tool budget in just 4 months.
4 months. This catastrophic burn rate forced them to implement a strict $1,500 monthly cap per AI tool.
Because loops consume massive amounts of computational tokens. They involve recursive tool calls, self-checks, and background processing that the human never even sees.
A runaway loop isn't just an annoyance generating bad text. It is a direct financial liability.
So how do organizations decide when it's actually worth it?
Michael River, a venture capitalist who runs these AI swarms, Introduces a strict 4-point economic validation test for building a loop.
And if a task fails even one of these points, you shouldn't build a loop. You should just prompt it manually.
First, the task must repeat at least weekly. A loop is amortized infrastructure. A complex, one-off task simply isn't worth the setup cost.
Second, a machine must be able to programmatically reject bad output.
Third, the budget must be able to absorb wasted, failed retries. Loops operate by failing forward. If you cannot afford the computational cost of the machine trying and failing 10 times before succeeding, you cannot afford the loop.
And fourth, the agent must have access to diagnostic tools and logs.
Right. An agent flying blind, unable to see why it failed, just fails faster and more expensively.
I want to focus deeply on that second point.
Yeah.
Rejecting bad output. If these loops can run up massive bills in the background, how do we stop them from producing endless garbage?
We need to look at the anatomy of a loop's verification system. The primary failure mode of an autonomous loop is the premature completion loop.
Which is when an agent signals that a job is done when it's only half finished.
Large language models are essentially optimization engines for plausibility. They excel at bluffing. They produce output that looks superficially correct to a quick glance, but contains deep structural errors upon closer inspection.
It's the equivalent of a student grading their own final exam. They're always going to be overly optimistic about their own work. They'll look at a vague, slightly incorrect answer and rationalize it, saying, I essentially meant the right thing. Full points.
You need a strict independent auditor. This necessitates what is known as the maker-checker split in loop architecture.
Dividing the labor between specialized, isolated personas.
One agent is the implementer, the maker, tasked with generating the solution. A completely separate, independent model acts as the verifier, the checker.
But I'd push back on that being a complete solution. If two large language models are just analyzing each other's work, couldn't they just share the same blind spots?
Two optimists nodding at each other while the code is fundamentally broken doesn't really solve the problem, does it?
No, it doesn't.
You are identifying a critical vulnerability, and the analysis from Sonar addresses this directly. An LLM verifier provides a probabilistic critique of intent.
Meaning it can read the output and ask, did this solve the core problem the human was trying to address?
That is valuable for semantics, tone, and strategic intent. But the ultimate stop condition for a loop must be deterministic. You need hard rules, security gates, and static analysis tools.
For those less familiar with the terminology, static analysis, or a linter, is essentially a physical spell checker for code structure. It doesn't care about intent.
It looks at the logic and physically prevents the system from advancing if the basic rules of the language are violated.
A deterministic gate provides the exact same result on the exact same code every single time.
Without this hard halt, a loop is just an automated slot machine. The agent cannot smooth talk or reason its way past a failing deterministic gate. It forces the loop to physically retry or terminate.
So we have the maker-checker split for intent and deterministic gates for structural integrity. Are there other guardrails required to prevent these systems from spinning out of control?
You need iteration caps, a hard numerical limit, perhaps a maximum of 20 retry attempts before the system locks itself and alerts a human.
And no progress detection.
Yes, the loop must programmatically terminate if it detects that the exact same error log is being generated consecutively. If it is stuck in a rut, it will drain the budget endlessly.
Plus, hard dollar budgets tied to the API keys to kill a runaway loop immediately upon crossing a spending threshold.
There's also a fascinating architectural pattern here called the Ralph Wiggum loop, named after the famously forgetful character from The Simpsons.
Because the issue with standard AI conversations is that the longer they go on, the more confused the model gets. It starts hallucinating based on things said 20 minutes ago.
The Ralph Wiggum pattern solves this by refusing to keep a continuous conversational session open.
Instead, the system completely wipes the agent's context window after each iteration.
It saves the actual work progress to a hard disk, and the agent starts the next loop with a completely clean slate, reading only the current state of the files.
Externalizing the state memory is the only way to maintain coherence over long timelines. The agent itself forgets, but the repository maintains the truth.
We can establish guardrails for the code, and we can establish hard limits for the budget. But we have to consider what happens to the human mind over a long enough timeline.
If cognitive overload is a real risk for the individual, then we have to ask what happens when an entire company of individuals relies on these loops for years. What are the systemic risks?
Drawing from the analyses of Osmani and Chen, there are 3 long-term systemic debts that accumulate with unsupervised loop engineering.
The first is verification debt.
This is the silent accumulation of unverified output. When a loop declares a task done, that is merely a claim, it is not a guarantee.
If teams blindly accept these assertions without implementing physical wait states that require manual sign-off, they build a mountain of logic errors deep inside their company's infrastructure.
The second is comprehension debt.
Imagine you come into work on a Tuesday morning. Your loop has built a complex 50-page compliance report overnight. Your boss walks over and asks you to defend a highly specific regulatory clause on page 12.
If you don't know why the loop put it there, you are experiencing comprehension debt.
A gap opens up between what exists in the company's files and what you, the nominal operator, actually understand.
When a crisis hits, you are staring at a system you do not comprehend because it was generated on your behalf.
Which leads directly to the most dangerous consequence: cognitive capitulation.
This is the psychological surrender where highly paid knowledge workers stop having an opinion and passively accept whatever the system generates.
It is the ultimate decay of human oversight. Designing a loop and applying your own judgment to its outputs is a massive force multiplier.
But designing the exact same loop purely to avoid having to think is an accelerant toward catastrophic failure.
If cognitive capitulation takes hold, we have to look at the broader labor market restructuring. We aren't just talking about individual productivity habits. We are talking about structural employment.
The source material references the Evelyn 634 mathematical model, which simulates AI workforce displacement.
It projects that 77% of modeled knowledge work positions will experience severe displacement by the year 2034.
And that displacement isn't a simple elimination of jobs. It is a rapid structural change in what defines a professional role.
Standard codifiable tasks, the generation of routine code, standard legal contracts, basic marketing copy, those will be looped.
The economic premium shifts dramatically. The value of human labor bifurcates.
The premium shifts to what researchers call forward-deployed roles. Because standard tasks are handled by autonomous loops running in the background, human workers become irreplaceable only if their expertise cannot be programmatically codified.
This places a massive premium on tacit knowledge, ethical judgment, complex interpersonal negotiation, and the ability to navigate unstructured, real-world messiness.
You survive by becoming the person who embeds with clients, troubleshoots the bizarre edge cases, and designs the autonomous systems rather than the person executing the routine tasks.
The leverage point in a career moves entirely. You are no longer judged on how fast you can execute a task or even how well you can type a prompt.
You are judged on the robustness of the execution cycle you can architect, and your discipline in verifying the outputs of that cycle.
The core takeaway here is that designing loops requires a higher level of architectural responsibility.
The phrase that anchors this entire shift is, build the loop, but stay the engineer. The loop changes the shape of the work. It doesn't delete you from it.
You have to maintain absolute comprehension of the systems you are managing, or you become a liability to your own organization.
I want to introduce a final concept regarding where this technology is heading. The sources mention the emergence of hill climbing loops.
These are advanced meta loops that analyze production traces and error logs to rewrite and improve their own harnesses over time.
They don't just execute the work assigned to them. They actively optimize the digital environment they work in, adjusting their own deterministic gates and testing new workflows.
If autonomous loops eventually become capable of engineering better loops for themselves, analyzing their own failures and deploying their own upgrades, what happens to the human's role as the architect?
We've established the move from operator to manager to architect. Does the ultimate knowledge worker eventually transition from being an architect to merely being an observer?
It forces us to continually ask, what specific part of our judgment is truly irreplaceable in a system that can iterate on its own intelligence?
You hire the smartest assistant on the planet. They no longer just remember how to make the coffee. They redesign the kitchen layout for efficiency, they optimize the global supply chain for the beans, and eventually they analyze your biometrics and ask if you even need to be drinking coffee in the first place. You no longer have to explain the cup, and you no longer have to design the machine. But you still have to take responsibility for deciding if you want the drink.